Okay, we'll go ahead and get started. Can everyone hear me and see my slides?
Yes.
Thank you. So believe it or not, today is the last lecture that we'll have for the semester. So today we'll finish chapter 10, and then on Wednesday will be exam 5, and exam 5 will cover chapters 9 and 10. I went ahead and posted the answers to the quiz 5, which was that take-home quiz that you did over the holiday. So I'm not going to go through it. I think it's, if you read the answers, it's self-explanatory. The other thing I wanted to mention was the final exam for this class will be Monday. So next Monday, December 7th. And it's at 8 a.m. So once again, it'll be online. So at 8 a.m. the exam will be posted. Any questions about any of that stuff? Okay, let me go ahead and get started here. So last week we started talking about gases, and we did some initial stuff with just some of the properties of them, and we started talking about relationships between gases and temperature, pressure, things like that. So we're going to continue on with that discussion today and finish that off. The next thing I'd like to talk about is something called Charles's law. And Charles's law states that if you have a fixed amount of gas, and by fixed amount we mean a constant number of moles of gas, and if you have that at constant pressure, the volume of the gas is directly proportional to its absolute temperature. And so this little cartoon balloon thing on the right hand side there is simply saying that if you keep those things that I mentioned constant and you heat it up, it'll get bigger. If you cool it down, it'll get smaller in terms of the volume. So it kind of makes sense. One thing to remember is that, as we said the other day, when we're talking about these different calculations with the gases, we need to express the temperature in degrees Kelvin. And it's no different for this one as the others that we've mentioned so far. So once again, if the temperature of a gas is increased at constant pressure, its volume will increase. And the mathematical relationship for that is, we see here V1 over T1, so that initial volume and temperature equals V2 over T2, so that subsequent volume and temperature. What this means is that as molecules absorb heat, they'll occupy a greater volume. So an example of this type of problem would be if we had a balloon that was initially at 25 degrees C, and that volume was 3 liters, what would its volume change to if we kept the pressure constant but dropped the temperature down to minus 15 C? So we'd solve this by defining what our initial volume and temperature were. So in this case, V1 is 3 liters, T1 is 25 degrees C. V2 is the volume that we're trying to find, so that's the unknown. And then T2 is minus 15 degrees C. Charles's law tells us that V1 over T1 equals V2 over T2, but we need to remember that to use this relationship, we need to convert temperature into Kelvin. So to convert into Kelvin, we take the degree C value and add 273 to it, so that T1 value is now 298 Kelvin, and the T2 value is now 258 Kelvin. If we plug in our V1 and then our two temperatures expressed in Kelvin, and we rearrange that to solve for V2, we see that gives us V2 equals T2 times V1 divided by T1. Plug in those numbers, that's the 258 and 298 Kelvin for the temperatures and 3.0 liters for the volume. And we plug those numbers in and then do the math, and we get 2.6 liters. So sometimes we're interested in seeing what changes occur when more than one of the properties of a gas changes at the same time. And we get something that's called the combined gas law, and that comes about by combining Boyle's law, which we talked about the other day, and then Charles's law, which is the one we just reviewed. So combining those Boyle's and Charles' laws equations, we get the equation we see here of P1 times V1 divided by T1 equals P2 times V2 divided by T2. So in this case, we see that if we have any changes in pressure, volume, or temperature, we can see what that effect is on pressure, volume, and temperature of the second set of conditions. So let's look at an example of this type of problem. So if we have a weather balloon and it's inflated to a volume of 53.0 liters, and the pressure is 1 atmosphere, and the temperature is 25 degrees C, then the balloon goes to a different altitude, and there the pressure drops to 0.40 atmospheres, and the temperature drops to minus 20 degrees C. What would be that volume of the balloon at this second altitude? So once again, we would go ahead and we would define what our P1, V1, and T1 were in the problem. So that was the 1 atmospheres, the 53 liters of volume, the 25 C temperature. And then our second set of conditions was 0.4 atmospheres. We're trying to determine what that new volume is. And then, so that's the unknown. And then T2, that second temperature, is minus 20 degrees C. Once again, we need to remember that we want to convert our temperatures to Kelvin. So we add 273 to each of those degrees C values. And that changes that T1 value to 298 Kelvin and the T2 value to 253 Kelvin. If we rearrange that combined gas law to solve for V2, we would have P1 times T2 times V1 divided by P2 times T1. So we would then plug in our P1 value of 1 atmosphere, our T2 temperature value, and that's 253 Kelvin, and then our V1 volume, which is 53 liters, and then divide that by P2 value of 0.40 atmospheres times T1, which is 298 Kelvin. We go ahead and have those numbers, we do the calculation, and we get 1.1 times 10 to the second liters. So we've looked at 3 different versions of these gas calculations, and a couple things. One is remembering which one is the correct one to use, and we can usually figure that out by looking at the information that we're given. So in this case, we were given pressure, volume, and temperature. And so we look at our formulas that we have a choice of, and this combined gas law is the one that has all three of those variables in it. So we knew we wanted to use that. The other key thing is just keeping straight which ones are the initial, so the P1, V1, T1, and which are the second. So that's the ones with the 2 subscript, making sure we have those set up correctly. And then finally, probably the thing that a lot of times people forget is usually the temperature is given in degrees C, but for the purpose of the calculation, we need to convert it into Kelvin. So we want to remember to add that 273 to the degree C values before we plug them into whichever formula that we're using. All right, at a given temperature and pressure, volume of gases that interact with each other is in small whole numbers. So for instance, 2 volumes of hydrogen gas and 1 volume of oxygen gas will make up 2 volumes of water vapor. So here, if we do have some type of reaction taking place with gases, just as we talked about in our regular reaction stoichiometry, reactions with gases also are stoichiometric. So remember, when we talk about stoichiometry, we're talking about those coefficients in front of each of the molecular formulas. So there's something called Avogadro's law. And what this tells us is that the volume of a gas at constant temperature and pressure is directly proportional to the number of moles of the gas. So at standard temperature and pressure, remember we said that at standard temperature and pressure, that pressure is 1 atmosphere, and then 25 C is the temperature. 1 mole of any gas occupies 22.4 liters. So what this means is that volume equals some constant, because we've got the 22.4 liter, we've got a standard temperature, standard pressure, all those are going to not change. That's what the constant represents. So the volume equals that some constant value times the number of moles. Or in other words, V1 over N1 equals V2 over N2. So we see that volume of gas in this formula tells us that the volume is directly proportional to how many moles of the gas that we have. The other thing I want to just mention, and we see that over here in the figure on the right, is that in each case, we have 1 mole of these gases, whether it's helium, nitrogen, or methane, the 3 examples here. We see that the mass is different. So you see the mass for helium 4 grams, N2 28 grams, CH4 16 grams. So the mass goes back to either the atomic or molecular weight. So that will vary, but in each case that represents 1 mole. Because that each represents 1 mole, the number of gas molecules is the same in each. And remember, number of molecules goes back to using Avogadro's number, 6.02 times 10 to the 23rd. 1 mole of gas, 1 mole of anything has that many molecules. So don't forget those things. We learned those a while back, but just remember that that relationship between 1 mole and number of molecules, and then how the molecular weight or molar mass fits into it as well. So there is some homework problems similar to the examples that we worked. And so go ahead and take a look at those. Any questions about this first part before we move on to the next part? Okay. So we talked about Boyle's law, Avogadro's law, Charles's law. And we saw some relationships between volume and pressure, volume and temperature, volume and number of moles. And so we can take all these relationships and we can combine them. And if we do, we get that volume is proportional to the number of moles times the temperature divided by the pressure. Okay, so that relationship just comes from taking those three that we have up top there and combining them. So that tells us that it's proportional. If we want to calculate out what some of these actual values are, then a proportionality constant, which we'll call R, was developed. And so that's called the ideal gas constant. And so if we then incorporate that ideal gas constant R and then kind of rearrange the equation, we see that PV, we get the relationship PV equals nRT. So pressure times volume equals the number of moles times the constant times temperature. And this is known as the ideal gas law or ideal gas equation. So this ideal gas constant R has several values, and it just depends on what units you're using. That first value, the 0.08206, and the units for that are liters atmosphere divided by moles Kelvin. That is by far the one that's usually used, the most common one. So pretty much all the work that we do, that'll be the constant that we'll be using for our ideal gas law calculation. And that's because our pressure is almost always going to be in atmospheres. We'll be working in moles, Kelvin. So if you do have some other units, these other constants that are used, but really the difference in the constants is just converting between the different units. For us, let's focus on that first one, liters atmosphere divided by moles Kelvin. And the nice thing about constants, we've talked about this when there's been other formulas that have had constants in it, is the constants help remind us of what the units of the other variables in the equation should be. So if we look at that first expression of the ideal gas constant with the liters atmosphere, moles Kelvin. So remember that dash there does not signify subtraction. It just means they're both there. So that would tell us that our pressure had to be in atmospheres, our volume had to be in liters, our the moles in moles, of course, and temperature would be in Kelvin. So that's one nice thing about the constants is that the units of the constant guide us on what the units of our variables in our equation need to be. So when you use this ideal gas law, usually you're given 3 of the 4 variables: pressure, volume, number of moles, and temperature. You know your gas constant value, and then you solve for your unknown. So you also can use this relationship to express density of gases. And remember, density of gas is weight per volume, right? So it's no different for gases. Density is still mass per volume, weight per volume. And so we can rearrange this ideal gas law to get an expression for density for gases. And so let's take a look at that. So we remember, once again, that the ideal gas equation is PV equals nRT. And if we divide both sides of this equation by V and by RT, then we get number of moles divided by volume equals pressure divided by the constant times temperature. Remember that moles times the molecular mass or the molecular weight equals mass. Because remember, molecular mass would be grams per mole. So moles times that would give us mass. So if we designate the moles as that small n, molecular mass by the capital M, and then the mass by the small m. So remember that. So we did that rearrangement above. And then if we multiply both sides by the molecular mass or the molecular weight, then we get that mass divided by volume equals molecular mass times pressure divided by the gas constant times temperature. Remember, mass divided by volume is our definition of density. So we can then substitute that mass per volume for D to signify density. And that leaves us with density equals the molecular mass or molecular weight times the pressure divided by the gas constant times temperature. So we're able to use that ideal gas law, that ideal gas equation. By doing some rearrangements, we can get a relationship between density and molecular mass, pressure, and temperature. So just to kind of talk about this a little bit more. So if we only need to know the molecular mass, the pressure, and the temperature to calculate the density of a gas. If we know the mass, the volume, and the temperature, we can calculate the molar mass. So what we see is by rearranging some of these things and by knowing these relationships that we talked about here, so in other words, things like moles times molecular mass equals mass, and mass per volume is density, things like that. By knowing some of those things, we can then determine what the molecular mass of a gas is if we have some information like mass, volume, and temperature. When we talk about chemical reactions of gases, similar to solution reactions, we'll have a balanced equation, and the stoichiometry of that balanced equation tells us the relative amounts of moles in the reaction. And so for gases, it's no different than for the other balancing equations that we did before. We have to balance the atoms on the products and the reactant sides. We do that by, after we write the molecular formulas out for each of the compounds, we do that by adjusting those stoichiometric relationships, those coefficients in front of each of the reactants and products. So there's some homework associated with this. I'd like to go over a couple of the problems. So let me pull up the questions here. So the first one I'd like to take a look at is question 1037. And in that one, we're being asked, calculate the number of molecules in a deep breath of air whose volume is 2.25 liters at body temperature, which is 37 degrees C, and a pressure of 735 torr. So we want to take a look at what's our volume value. In this case, we're told it's 2.25 liters. Our temperature value, which we're told is 37 degrees C. We know that we want our temperature in Kelvin. So we're going to convert that to Kelvin. And by adding 273 to the 37 degrees C value, and that tells us our new temperature, the number we're going to use in our calculation is 310 Kelvin. The pressure was 735 torr. We want our pressure to be in atmospheres because remember we said we're going to be using that 0.08206 gas constant value, ideal gas law constant value. And that had units of liters, atmospheres, mole, Kelvin. So that tells us we can't leave this in torrs. And so 1 atmosphere is equal to 760 torr. So if we take the 735 torr and divide it by 760 torr, that converts it into into atmosphere units, and that value is 0.967. So we look at our ideal gas law equation. That's the PV equals nRT. And so our pressure, we've got that in atmospheres. So that's great. That's the 0.967 value. Our volume started in liters, so we're good there. So that's 2.25. That equals, well, we're trying to find the number of molecules. But remember we said before, when we were a few slides ago, that we know that we can change moles into molecules by using Avogadro's number. So for now, we're going to solve and calculate a number of moles, and then we can convert later into molecules. So N is what we're trying to find in this case, number of moles. Next we have R, and our constant value is 0.08206. And then finally, temperature in Kelvin is 310. So if we go ahead and plug those numbers in and then solve for N, we get 0.0855 moles. So we're not quite finished yet because the question asked us for the number of molecules. So if we say that we have 0.0855 moles, we know that there are 6.02 times 10 to the 23rd molecules per mole. That's from Avogadro's number. So if we do our dimensional analysis to convert the moles into molecules, we need to multiply 0.0855 moles times the 6.02 times 10 to the 23rd molecules per mole. We go ahead and do that math, and that leaves us with a 5.15 times 10 to the 22nd molecules. So once again, by looking at the problem, we saw that we could use the ideal gas law equation to do our calculation and find number of moles. And then we could convert number of moles into molecules by using the conversion with Avogadro's number. We had to do 2 changes to some of the information that we were given in order to get the units to line up with the units in our gas constant. So once again, we had to convert temperature from degrees C to Kelvin, and we had to convert the pressure from torr to atmospheres. So we used some conversion factor type stuff in order to do that. Once we did that, we had our equation in a form with the right units based on that constant that we were using, and then we solved for the moles. And then once again, as I said, used Avogadro's number to convert from moles to molecules. So a couple things going on here. Key things, once again, keep the units straight, and then remember back that we have a way, if we have moles, to get to molecules and vice versa, and that's the Avogadro's number. Okay, in part B of the question, it says the adult blue whale has a lung capacity of 5 times 10 to the 3rd liters. And it says calculate the mass of air and assume the average molar mass or molecular weight is 28.98 grams per mole. And that's calculate the mass of air contained in adult blue whale's lungs at 0 degrees C and 1 atmosphere. And once again, we're assuming ideal behavior, so we can use that ideal gas law. So let's look at what we were given. We were given volume, 5 times 10 to the third liters. We were given temperature, 0 degrees C, and we're giving pressure of 1 atmosphere. So, and we're talking that we're wanting to get a mass of air. So we know that mass, molar mass, molecules, all those things can be interrelated. And so when we look at the ideal gas law, we have a volume value, we have a pressure value, we have a temperature value, we have a constant. So the only thing that we don't know is the number of moles. So let's go ahead and solve for the number of moles. And then once we get that, then we can figure out how to change those moles into grams. So we know that our pressure needs to be in atmosphere. And it is, so we're good there. So we have 1 atmosphere. We know our volume needs to be in liters. Once again, we were given information in liters, so we're good there, 5 times 10 to the third liters. Moles is what we're trying to find. That 0.08206 is our constant that we're using, and those units are liters atmosphere divided by moles Kelvin. So then the last thing is to get our temperature into Kelvin. So 0 degrees C, we would add 273 to that to convert it to Kelvin. And now we're at 273 Kelvin. So we can plug that in. So we can plug all those values into the PV equals nRT equation. And then we can solve for N, which will be number of moles. So if we do that, we get a value of N of 223 moles. So if you have 223 moles and you want to get to grams, because in this question, they're saying calculate the mass of air. So mass of air tells us they want to know how many grams of it. But they also gave us a clue in that they said the molar mass, the average molar mass is 28.98 grams per mole. So if we have 223 moles, we want to convert that to grams, we can use this molar mass, this molecular weight value, and by having the grams value in the numerator, moles value in the denominator, then we look at our dimensional analysis and we get the moles canceling each other, and we're left with units of grams. And so if we go ahead and do that math, we get 6.46 times 10 to the third grams. Any questions about either of these two calculations? Okay. Let's do another one of the homework problems. Let's take a look at 10.51. Let me find that one here. Okay, in 10.51, they're asking us calculate the density of NO2 gas at 0.970 atmospheres and 35 degrees C. So a couple things that we needed to do. We needed to remember that density is typically referred to as grams per mil. It can be grams per liter also. But the key thing to do is remember density is weight per volume. If we then go and we go back to PV equals nRT, our ideal gas law, we see that we have a pressure value, we have a temperature value, we have a gas constant, and then we know that if we rearrange this so that we have moles divided by volume equal to pressure divided by the gas constant times temperature, that moles per volume is close to density, because we have a way to convert from moles to grams, because we're told it's NO2, so we know what the molar mass of that is. And so that would be the molecular weight. So it would be 1 times 14 plus 2 times 16 for a total of 46. So we'll be able to use that information to convert the moles into a grams value. And then, so if we have a grams value divided by what the volume is, then that'll get us into a density type of situation. So let's go ahead and plug and find the moles first, solve this moles per liter, and then we'll convert it over to a weight per volume. So using that P over RT equals number of moles divided by volume, we have 0.970 atmospheres divided by the gas constant times 35 plus 273 gives us 308 Kelvin. And we solve that and we get 0.0384 moles per liter. We want to convert that moles to a grams value, and we can go ahead and take 0.0384 moles times 46 grams per mole. Remember that 46 is our molecular mass from the molecular weight of NO2. And then we can convert, we have a choice here. We can either convert the liters in the denominator to milliliters. If we want to do that, then we know there's 1,000 mils equal to 1 liter, or we could just leave it as grams per liter, either way. If it's grams per mil, it's 1.77 times 10 to the minus third. If it's grams per liter, then it would be 1.77 grams per liter. Part B of this problem is similar. The only difference there is that you're calculating a molar mass, given some information. So it'd be a similar type approach. So I'm not let you do that one on your own. Okay, any questions about either of the calculations that we went through? Okay. So let's move on to Dalton's law of partial pressures. So if you have two gases and they don't react, so remember before we were talking about some things that react, but if they don't react, they're just combined in the container, then they essentially act as if they're alone in the container. So the total pressure of a mixture of gases that don't react is equal to the sum of the pressures that each one would exert if they were by themselves. In other words, that total pressure is just the sum of the individual pressures. So that leads us to talk about something called a mole fraction. So because each gas in the mixture essentially acts like it was alone, we can relate amounts in a mixture to partial pressures. And so this what looks like a real confusing formula here is simply just the P1 indicates and N1 indicates the pressure and number of moles of one of the gases. So R and T and V are going to stay the same because you have more than one gas in this same container. The temperature is the same, the volume's the same, the gas constant's the same. The only things that are varying are number of moles and then, of course, the pressure. And then the denominator with the T, PT, and NT, that just signifies the total pressure and the total number of moles. And so when you take these ideal gas laws for the individual gas and then the total, then what you see is that the gas constant, the temperature, the volume, those all cancel out. And so you're simply left with P1 over PT, the total, is equal to the number of moles of that gas divided by the total number of moles. So it becomes pretty simple. This, so this relationship of moles of one compound versus the moles of another is called the mole fraction. So this N1 over NT, so number of moles of one particular gas divided by the total moles, that's known as the mole fraction. So we go back and look at, so we had this P1 over P2 equals N1, N2. If we go ahead and rearrange that, so in other words, multiply each side by PT, then we get P1, so the pressure of one of them is equal to the number of moles of it divided by the total moles times the pressure, total pressure. That ratio of moles, we said, is defined as the mole fraction. So that can be rewritten as X1. So the mole fraction of that first gas that we're talking about times the total pressure. In the kinetic molecular theory for the gases, we have some observations that we talked about in terms of the gas laws. And so we're going to talk a little bit about what's going on in that. And so once again, we mentioned this early on, but pressure inside the container comes from collisions of the gas molecules. So in other words, gas molecules running into each other, and also from collisions with the walls. So in other words, the gas molecules running into the sides of the container. So some of the basic ideas of this theory is that gases have large numbers of molecules that are having continuous random motions. In other words, they're moving around all the time in whatever container it is. And so there's a bunch of them moving around. One thing is, though, is that if you look at the volume of all those molecules, it's pretty small compared to the volume of the container. So in other words, think of it as if you had, 10 people and put them in a big auditorium and they're running around. Well, the odds of them running into each other, it can happen, but it's not as common as it would be if it was a smaller container or something like that. So the forces, so you do have you can have attraction or repulsion type forces between the gas molecules, but because there's all this open space, those forces usually are not real strong. When you do have a collision, you do get a transfer of energy. But as long as you don't change the temperature, it really doesn't, that average kinetic energy really doesn't change much with time. That average kinetic energy of the molecules is proportional to the temperature. So temperature goes up, that kinetic energy increases. Usually it goes down, it goes down. So we see some examples of this. So we see information about speed and kinetic energy. Speed and kinetic energy, there's a slight difference in those, but those are similar type values. We're not going to really get into the exact difference today. But just remember, as you increase the temperature, the speed, the kinetic energy increases. And we see this on the first plot on the left. So the blue plot is the degree C values. And then we see the red plot is at 100 degrees C. And on the x-axis is the molecular speed. And so what you see is that apex in the plot shifts to the right. So in other words, shifts to a higher molecular speed as you increase the temperature. So that's kind of what you would expect based on what we've talked about. The other thing that we know, and here's an expression for that, is we know that if a gas has a low mass, its speed will be greater than the speed of a heavier molecule. And so in this plot, we see an example of that. So you see oxygen, nitrogen, water, helium, hydrogen. We see all these in gas form. And if you were to sit down and calculate out the molar mass of each of those, you would see that hydrogen, H2, and that's the one because on the x-axis is the molar speed, so that's its apex has the highest molecular speed. So you would see that that one has, because it's the smallest, has the lowest molecular mass, it has the highest molecular speed. And oxygen, which has a molar mass of 32, is the heaviest of these molecules, and so it has the slowest speed. So just in general, what this formula is telling us, and you can calculate it out if you want, but what it's telling us is if the gas has a lower mass, its speed is greater than that of the speed of a heavier molecule. If we have an increase in volume at constant temperature, this causes the pressure to decrease. And you think about that. Think of it as you're going to have fewer collisions with the walls. You're going to have fewer collisions with the other molecules. And it's just that same concept of if you have, say, 10 people in a room, and then you take those same 10 people and put them in a bigger room, then you're just going to have less collisions with the walls, less collisions with each other. If you keep the volume constant, it increases that temperature. This is what we were talking about. The pressure is going to increase because you're speeding things up. And as you speed things up, that's that kinetic energy increasing. As you speed it up, then you're going to have more collisions with the walls, and you can have more collisions with the other molecules. So there's two terms that we talk about when we talk about gases moving. One is effusion, and the other is diffusion. So effusion is the escape of gas molecules through a tiny hole into an evacuated space. So we see a nice drawing of this. And so we have a bunch of gas molecules that are in the top part of this cylinder. We have a little bit of a hole, a little pinhole there. And then there's a vacuum down there, so there's no pressure preventing it from going down in there. Well, the molecules have to bounce around and have to hit the opening in that small hole for them to effuse, to escape through that hole. So that process is the effusion process. Diffusion is similar, but it is slightly different because of the definition. And so diffusion is when you have a gas that's put into a space, and then it needs to spread out through that space. Okay, and this could be one gas, this could be more than one gas, it doesn't really matter. It's just you introduce something into a space, and then it's got to diffuse. You think of what that word means. It's got to move about so that it's in all portions of the container now. So effusion has this where the molecules are bouncing around and they've got to hit that particular hole. Diffusion, there's no evacuated space that it's going to, there's no hole it's got to go through. It's just you introduce it into the container, so to speak, and then it's got to just spread out through the container. So something called Graham's law describes how these do this from a mathematical perspective. And what it does is it relates the molar masses of the two gases to their rate of speed of travel. So lighter gas always has a faster rate of speed. Remember, we talked about that just a few moments ago. And so we have an equation of R1 over R2 divided by M2 times M1. As we said, lighter gas always has a faster rate of speed. When we start getting some molecular collisions, then it kind of complicates the process a little bit. Diffusion rate of gases is slower than the molecular speed. And because of the collisions, the direction of motion of a gas is constantly changing. So it goes along for a while, doesn't hit anything, but then it hits something and then it changes its direction. So you have just the diffusion itself taking place of the gas. If nothing, it was never hitting another gas molecule, but it does hit some other gas molecules once in a while, and that changes things. So the average distance traveled by a molecule between collisions is defined as the mean free path. So the gas molecule will go and move along for a certain amount of distance before it hits another molecule, and that distance is the mean free path. So the example we have here is, think of it working your way through a crowd and getting bumped. So you're trying to cross a room, and you know where you're going and you're headed towards it, and you walk for a period of time without anyone getting in your way, but then at some point you bump into someone and maybe it causes you to go in a slightly different direction. That's the kind of thing we're talking about with gases. So in the real world, gases conform to that ideal gas equation only at relatively high temperatures and low pressure. So it's a good guide to give us a feel for it, but it's not perfect in kind of normal type of situations. So we're not going to get too bogged down on that, but we did just want to mention it a little bit. When we talk about that ideal gas law, there's some assumptions that we make, and one is that the gas molecules have negligible volume, and that there's no attractive forces between the gas molecules and things like that. So the ideal gas law really is based on those gas molecules being pretty independent of everything else. And in reality, that isn't exactly true. So when you get away from some of those ideal conditions, then there are some other factors that come into play. You can adjust the ideal gas equation to take into account some of the deviations. And one of these equations that it does some adjustment is something called the van der Waals equation. So there's a pressure adjustment that's made in the equation, and that's due to the fact that molecules can attract and repel each other to some degree. And then there's a volume adjustment due to the fact that the gas molecules do take up some space. So instead of saying it's nothing, it takes into account what that value might be. And so here we see what that rewritten equation looks like when you take into account those adjustments. So instead of PV equals nRT, we have P plus this N squared times A over V squared times V minus NB. And so the A term is a term for how strongly gas molecules are attracted to each other. The B term is a measure of the volume of that the gas molecules actually take up. And as you would think, larger molecules have larger volumes and tend to have greater intermolecular attractive forces. The table here actually has some of what these constant values are for a few gases. And so you can what you would do is you would use those values and plug them in to that equation for the A and B terms to get a more accurate calculation than the standard ideal gas law. Just want to point this out. We're not going to worry about this in the class. We're going to stick to the ideal gas law when we do our calculations. But this is just to let you know that ideal gas law is pretty good, but when you look at it a little more closely, some of the assumptions that you make about interactions and things like that and volume that the gas molecules take up, those aren't 100% correct. And so people have done some work to try and understand that a little better. Okay, let's go over a homework problem here. And let's look at 10.63. So in 10.63, we're told we have a mixture containing 0.65 moles of helium, 0.330 moles of neon, and 0.110 moles of argon. And it's in a 10-liter vessel at 25 degrees C. And then we want to calculate the partial pressure of each gas and then the total pressure of the mixture. So remember, we said that if the gases aren't reactive, and these are non-reactive gases, then the total pressure is just the sum of the individual pressures of each of the gases. So in this case, what we can do is we can go ahead using the ideal gas law and calculate out what the pressures are for the helium, the neon, and the argon. Those would be the individual pressures. And so that's our partial pressures for each of those gases. And then to get the total pressure of the mixture, we would just add those three values up. So that's what we're going to do. So PV equals nRT. We know our pressure needs to be in atmospheres. And so that's what we're going to be solving for. Our volume needs to be in liters. It was given to us as 10 liters. So we're good there. We have the number of moles of each of these. So we have that value for N, so that's great. The R value is our constant, our 0.08206 value. And then the last thing we need is temperature. Temperature was given in degrees C. We want to convert that into Kelvin by adding 273. And that brings our temperature to 298. So let's do helium first. So we go ahead, we have pressure times 10 liters equals the moles of helium was 0.765 times our gas constant, and then times 298. We solve for that pressure value and we get 1.87 atmospheres. We do the same type of calculation for neon and argon. And so the only difference there is that we substitute out those numbers of moles for neon and the number of moles of argon. So if we do those two substitutions, we see for neon, the pressure is 0.807 atmospheres, and for argon is 0.269 atmospheres. So we do this calculation for each of the gases. Those are our partial pressures. We remember that P total equals the sum of the individual pressures. So then if we add those three partial pressures up, we get 2.95 atmospheres. So once again, as we've done with some previous calculations, we need to identify which formula is the one that we want to use. A lot of times we can figure that out by just seeing what variables we were given. In this case, we were given moles, and we were given temperature, and we were given volume. So we could see that by using ideal gas law, we could then solve for pressure and get those pressure values. The other key thing was making sure our units were all correct. So we checked those, and then the one that wasn't in the right units, in this case, it was temperature. We went ahead and converted that degree C unit into Kelvin so that our formula worked. And just to repeat it once again, one key thing that helps us with understanding the units that we need to be in is looking at that constant, this gas constant, and seeing the units that the gas constant is expressed in, and knowing that the other variables have to line up so we're canceling units out from that constant value. That allowed us to get those partial pressures, and then it's just simply remembering that for gases, the total pressure is just the sum of the individual partial pressures. Okay, so that's it for this chapter. I would suggest that you go and take a look at some of the homework problems, get comfortable doing some of these calculations. On Wednesday of this week, as I said earlier, we'll have an exam on chapter 9 and chapter 10. And then after that, on the Monday, the 7th, will be the final exam, and that is at 8 o'clock. So it's a little bit earlier than our normal class time, but that's the time they gave us. So 8 o'clock is the final, and that will cover all the chapters 1 through 10 that we went through this semester. Any questions about any of this stuff? Okay, that's it for today. And if anything comes up and you need to contact me, just send me an email or something. Thanks.
Will we be using the same textbook for next semester?
Yes, you will.
Okay.
Yeah, so if you have the textbook, hold on to it. You'll be using that for next semester. And it's just a continuation from there. Okay, any other questions? Okay, thanks.